Today I'm going to teach you machine learning using a tree. Yeah, you heard me right. Not a textbook, not a robot, a literal tree. And by the end of this video, you'll finally understand how AI actually learns. First up, we have supervised machine learning. So what is supervised machine learning? It is data that has been labeled for training. It's used to train models, and features and labels are studied in past observations so unknown labels can be predicted for future cases. The user knows the labels and you want a very exact outcome. It is task driven, making a prediction and receiving back a value. Some examples of this are classification and regression. Next up, connected to supervised machine learning, we have regression. So, regression is a form of supervised machine learning. It is the process of finding a function to correlate a labeled dataset into a continuous variable or number. Let's predict the temperature variable in the future. What will the temperature be next week? An example we have is 80 degrees Fahrenheit. Dots, also known as vectors, are plotted on the graph in the x and y axes. The regression line is drawn through the dataset, as you can see in the picture. So we can also find the vector's distance from the regression line, also known as error. Different regression algorithms use error to predict future variables. We have mean squared error, root mean squared error, and mean absolute error. You can see how each dot differs in the distance from the main regression line. In real-world scenarios, a data scientist will use an iterative process to repeatedly train and evaluate a model, which can vary. Feature selection and preparation, choosing which features to include in the model, including calculations applied to them to help ensure a better fit, algorithm selection, like algorithms other than linear regression, and algorithm parameters, numeric settings to control algorithm behavior, more accurately called hyperparameters, to help differentiate them from the x and y parameters. After multiple iterations, the model that results in the best evaluation metric acceptable for the scenario, depending on the situation, of course, is selected. Next, we have classification, which is also connected to supervised machine learning, in that we have binary classification, first up. So binary classification determines whether the observed item is or isn't an instance of a specific class. Put another way, it predicts one or two of mutually exclusive outcomes. So some examples of this are credit card fraud detection, as a transaction can be classified as fraud or legitimate, email spam detection, which can be classified as spam or not spam, medical diagnosis, as a patient's systems can be used to predict whether they have a disease or are healthy, and quality assurance, whether quality specifications were met can be determined. So next in binary classification, we have a step in calculating evaluation metrics for this binary classification model. The first one is that it visualizes model predictions, what is predicted, versus ground truth labels, what is actual. The arrangement is that the correct or true prediction shown in a diagonal line from top left to bottom right. An example is shown on the next slide. Often, color intensity is used to indicate the number of predictions in each cell, and a quick glance at a model that predicts well reveals a deeply shaded diagonal trend. So it is a matrix of the number of correct or incorrect predictions for each possible label, this first step, also known as the confusion matrix. So you can see a visual representation over here. There will be exam questions that ask you which values are false positives and false negatives. 1 and 1 would be true positive, and 0 and 0 would be false negative, like the lines show below. The arrangement of the confusion matrix is that such true predictions, which are correct, are shown in a diagonal line from top left to bottom right, and the diagonal from top right to bottom left would be incorrect, also known as false predictions. You can look at this model more clearly below. Note that we have 130 total items. Also note that the matrix size is dependent on these labels. We can see that the three flowers, lilies, dahlias, and roses, would be 3 times 2, which equals 6 cells. They will ask the size of this matrix. Here we have 2 rows and 2 columns, say of lilies and dahlias, but if we had 3 of lilies, dahlias, and roses, it would be calculated as shown in the top left. Next, we have multi-class classification, which ties back to classification, which further ties back to supervised machine learning. In multi-class classification, it extends binary classification to predict a label that represents one of multiple possible classes and follows the same iterative train, validate, and evaluate process as regression and binary classification. It is a subset of the training data that is held back to validate the trained model. In most scenarios that involve a known set of multiple classes, it is used to predict mutually exclusive labels. For example, a shark cannot be a both breed tiger and great white, but some algorithms that can be used to train multi-label classification models could render more than one valid label for a single observation. For example, a podcast could potentially be categorized as both horror and comedy. Okay, coming up is unsupervised machine learning, the other form of machine learning that we will study in this section. So, in unsupervised machine learning, data has not been labeled. The ML model does its own labeling. The training models use data consisting only of feature values, without any known labels. The algorithms determine relationships between the observational features in training data, and the user doesn't know the labels. An outcome does not need to be exact values, like in supervised machine learning. It is data driven, which means it recognizes a structure or pattern. An example of this is clustering, which we will further investigate. Okay? So, in clustering, a part of unsupervised machine learning, it doesn't make use of previously known label values for training. The process is of grouping unlabeled data based on similarities and differences. A clustering model looks at the features of each data point and decides which group or cluster it best fits into. The number assigned to that group will be its label, and it's the way of identifying the cluster an observation belongs to. You can see an example of this over here on the right, of who recommends purchasing a Toyota car and who recommends purchasing a Mercedes car and how that pans out. Next, in clustering evaluation, you have multiple metrics that you can use to evaluate cluster separation, like the average distance to cluster center, which is the average distance of each point in cluster to the cluster centroid, the average distance to other center, which is how close in average each point in the cluster is to the centroid of all other clusters, and the maximum distance to the cluster center, the furthest distance between a point in the cluster and its centroid, a silhouette, which is a value between -1 and 1 that summarizes the ratio of distance between points in the same cluster and points in different clusters, which the closer to 1, the better the cluster separation. Clustering algorithms include k-means, k-medioids, density-based, and hierarchical, and there's no known label in which to compare the predicted cluster assignments, as the evaluation of a cluster model is based on how well the resulting clusters are separated from one another. That's it! If you enjoyed today's content and if it was useful, make sure to click the like and subscribe, and also check out my full AI 900 course in the description, which is now on discount, free for you to take a certification that matches your skills to industry professionals.